Okay, welcome back. We are in our fifth lecture and I will start sharing my slides. Now we are studying equations in one variable and looking for ways to find roots of these equations. We have looked at the very basic method in our last lecture, which is the bisection method. And now we are going to take a different approach. We are going to actually look at fixed points instead of looking at roots. But let me explain why we are looking at fixed points. So first of all, whenever you have a function which is defined on this closed and bounded interval AB, and it's taking values in the set of real numbers, then for a function like this, a fixed point is that point P with the property that f of P is P. So this is what we would think about a fixed point, that the function does not change the point. The function fixes the point. So this is what a fixed point is. And whenever you are looking for some root of the equation, whenever you are trying to solve the equation fx equal to 0, that is same thing as finding a fixed point for this new function gx equal to fx minus x. Or you may get a different function. From the equation fx equal to 0, you can get many functions whose fixed points will give you the root of fx. Instead of looking at fx minus x, you can look at x minus fx. You can look at x minus 2fx. You can look at a polynomial in fx with constant term being 0. You can have x minus fx whole square plus fx cube plus fx. That would also be another function whose fixed point will be a root of your function. So, all right. So maybe I should take that back. What you will have is that when you have a fixed point for such a complicated thing, it will be the root of the polynomial in fx. It will not necessarily be the root of fx. But if you also happen to take it to be a polynomial in fx with the zero term, zero constant term, I think it will be the root of fx. In any case, what you can do, certainly you can multiply fx by scalars, and you can either put plus or minus. So there are many ways. You will see that the roots of f correspond to fixed points of various functions that you have. Okay, so and moreover, fixed points are something which are studied very well in mathematics. So fixed points of several functions have been studied, and there are some nice results which guarantee the existence of fixed points. So we saw that the intermediate value theorem will tell you the existence of the fixed point, the existence of root of an equation. So similarly, there is a theorem which guarantees existence of a fixed point, and this is called the fixed point theorem. So it's a very basic theorem. It says that whenever you have a function defined on a closed and bounded interval, and if it takes values back in the same interval, and if your function is continuous, then it should have a fixed point. So any continuous function which takes the interval AB to itself should have a fixed point. And moreover, what we are later going to do is to try to get a sequence converging to the fixed point. So we are interested in checking whether the fixed point is unique. So if you also have that the derivative, in addition to the function being continuous, if your derivative exists on the interior, on the open AB, and the derivative satisfies this condition that its modulus is less equal k for all x in the interior, then f has a unique fixed point. So these are very nice theorems. So first of all, whenever you have a function from closed AB to closed AB, a continuous function, there has to be a fixed point. This is point number one. And moreover, with a condition on the derivative, we have that the fixed point is also unique. So we will not be proving this theorem very rigorously in this course, but actually the second part uses mean value theorem. Whenever you have two fixed points, then what you can do is that you can use the mean value theorem, and then you will see that fp minus fq upon p minus q is the function value at some other point, and so on, and then you can get a nice contradiction. And the first part is actually quite easy to prove. So I will leave the first part to you. It follows from the intermediate value theorem. You have to just basically observe some basic things and then it will follow from the intermediate value theorem. So, but we will use these theorems. We will see that these two theorem, these two parts of the theorem, which are actually two separate theorems, and those are very useful. And we will try to look for functions because we have seen that whenever you have a function whose root is to be found, you can convert it into a fixed point problem in many ways. And it would be nice to convert it to a fixed point problem which satisfies this condition. Okay, that's what we will try to look for. So let's see an example. Suppose I want to look at this function x square minus 1 upon 3. And this is the function which is defined on the interval minus 1 to 1. And we want to first of all check whether it takes minus 1 comma 1 to itself. And for that we compute the extremal values of this function. You know, we need to compute where the derivative vanishes, and in addition we have to look at the boundary points of the function. So those are the points where the maxima and minima will be achieved. So one sees that the maximum value is 0, which is achieved at both 1 and minus 1. At both the ends the values are 0, and the minimum value is minus 1 by 3 attained at x equal to 0. So it's like a part, it will look like the part of the parabola which is shifted slightly below. The usual parabola y equal to x square has x equal to 0, y equal to 0 as its minimum point. Here it is x equal to 0, y equal to minus 1/3. That's the lower point. So that's how it looks. The x-axis will intersect this parabola at the points x equal to 1 and y equal to 1. Okay, so this is what this function looks like. And therefore, the highest value is 0, the lowest value is minus 1/3, and therefore all the other values are between these. And therefore, the image is now contained inside minus 1 comma 1. So this function takes the interval minus 1 comma 1 to itself. Actually, it takes it to a much smaller interval, but it certainly can be thought of as a function from minus 1 comma 1 to minus 1 comma 1. Okay, and therefore the fixed point theorem will tell you that this function should have a fixed point in minus 1 comma 1. You can also solve for the fixed point. Moreover, the derivative property is satisfied because the derivative modulus is mod of 2x upon 3, and on minus 1 comma 1 it is less than or equal to 2 by 3, so it is less than 1. Therefore, there is a unique fixed point in minus 1 comma 1. So our excuse me. So our function x square minus 1 not only has a fixed point, but the fixed point is unique because the derivative is satisfying that condition, that mod of the derivative on the whole interval is bounded above by a constant which is less than 1. Okay, so if you wanted to find this fixed point, that can be computed because you will just put fx equal to x, which will give you that x square minus 1 by 3 is x, and if you write down this quadratic equation, which is p square minus 3p minus 1 equal to 0, and then we use our formula for solving quadratic equations, and we see that 1 by 2, 3 plus minus root 13, that is the solution. So these are the fixed points. These are two fixed points, I understand, but one of them is between minus 1, 1, and that is the fixed point which is 3 minus root 13 by 2. It's a negative number. 3 is the square root of 9. So we are subtracting square root of 13 from square root of 9. But 3 minus 13 root 13 by 2 is between minus 1 and 1. Okay. So this is the unique fixed point that we are looking for inside minus 1 comma 1. You may wonder about the other root, 3 plus root 13 by 2. This is outside our interval minus 1 comma 1, but it lies between 3 and 4. And if you were to look for the function x square minus 1 by 3 on that interval 3 by 4, it doesn't really satisfy the hypothesis of the above theorem. So the hypothesis is only a sufficient condition. It is not necessary. It is not necessary that whenever you have a fixed point, that condition has to be satisfied. Whenever the condition is satisfied, you will have a fixed point. So the condition is sufficient for the existence of a fixed point, but it is not necessary. Sometimes you may have a fixed point without that condition being satisfied, and that means that our theorem is not an if and only if theorem. All right, so those are the small points that we need to think about. In fact, there you will see that well, it should not be G, it should be F. G of 4 is 5 because if you look at 4, if you put x equal to 4, you will see that 4 square minus 1, which is 16 minus 1, which is 15 by 3, that is 5. So already G4 is 5. So your point 3 comma 4 is not taken to 3 comma 4, not by G but F. This G has to be F. And the derivative condition is also not satisfied. The derivative at the point 4 is 8 by 3, which is much bigger than 1. All right, so now we want to get a sequence which will give us the fixed point. Here we had a nice quadratic, and we could write that quadratic down and solve it to find the fixed point. But in general, our functions might be given by higher degree polynomials if they are given by polynomials. Otherwise, there could be exponential functions and so on, and then it will not be easy to solve the equations to find the fixed points. So we have to find a method to do it, and this is the method. It's a very nice method. What we do is that we start with a continuous function from AB to AB. All right, and you take any initial approximation, whatever initial approximation that you want to take, you take it, and then generate a function by applying the generate a sequence by applying the function f to the points that you keep getting. So once you have p naught, you get p1 by applying f to p naught, and then you get p2 by applying f to p1. Then p3 will be f of p2. So your sequence will be p naught, f p naught, f square p naught, which is f of p naught, f cube p naught, f power 4 p naught, and so on. Those are the entries in the sequence. So that is our sequence. Okay. Now this sequence might be convergent or may not be convergent. Even though what we know certainly is that the sequence is bounded because the function is taking the interval AB to itself. So the function sequence is bounded, but it can be an oscillating sequence. It may not really be convergent. However, if it converges to some point P, then we have got our fixed point because the function value at P is f of limit Pn, because P is the limit of the sequence Pn, right? So f of P is f of limit Pn, but f is continuous. Remember, we are always working with continuous functions. So because of the continuity of this function f, the f of limit is same as limit of f. So we have it to be equal to limit of f Pn. But f of Pn is Pn plus 1, and whenever you have a sequence which is convergent, you shift the sequence by a few places here and there, and you still get the same limit. So the limit of Pn plus 1 is again P. So we get that our P is the fixed point. So whenever you have this sequence Pn, which is a convergent sequence, then the limit of that sequence is your fixed point. So it's a very nice method actually, and you have to just ensure that your sequence is convergent. You can ensure that by a few more small observations. For instance, once you know that your sequence is monotone, it is a bounded sequence. Once you know it is monotone, it has to be convergent. Monotone meaning it has to be either increasing or decreasing. So whenever you have such a behavior of the sequence, your sequence is going to be convergent. Okay, so fixed point iteration, this is called fixed point iteration method because you are iterating the function on this point P naught itself. Okay, and then the limit point is going to be the fixed point. So this is one very simple-minded method, and it works quite well many times, but sometimes it may not work. And let's see an example to see what can happen. So suppose we are looking at this cubic equation now. Earlier we had looked at a quadratic where we could just solve the quadratic and get the fixed points. Here we have a cubic at our hand, and the intermediate value theorem will tell you that in this root 1 comma 2 there is a unique root. Okay, so once it converts to a fixed point theorem, then with some nice conditions, the fixed point will also be unique. That is what we are looking at. Okay, so this equation can be rewritten in many ways. You know, you can write it as x cube equal to 4x square minus 10. You put the 4x square minus 10 to the other side, so you will have x cube equal to 10 minus 4x square. Then you divide by x square throughout, and then you have some x equal to something. So you have some such ways to rewrite this equation, and therefore it can be converted into fixed point problems in many ways. So we will write three ways. These are the three ways, and let's just check that whenever you have a fixed point, we do get the root of our equation. So whenever we have this g1x, this is our function. So we will look at g1x, which is x minus x cube minus 4x square minus 10. So whenever you have a fixed point problem, so that means whenever you have equality for x equal to g1x, then you will have that this x cube plus 4x square minus 10, that is already 0. So maybe there is a sign mistake here. I should perhaps put plus 10 instead of minus 10. Okay, so x minus this side, this is to be subtracted, and therefore that minus 10 will become plus 10. Okay. On the other hand, if you have x equal to g2x, if you have a function g2 which is given on this right hand side, which is 10 upon x minus 4x and then the whole bracket to the power 1 by 2, the square root of this power whole bracket, if that is equal to x, then x square will be this bracket, right? So you have x equal to the square root of this bracket. So x square is this bracket. And so you can now multiply by that x in the denominator to all the sides. So you will get x cube equal to 10 minus 4x square. And you bring the 10 minus 4x square to this side to get x cube plus 4x square minus 10 equal to 0. So indeed the second equation, x equal to g2x, also this is the fixed point problem which gives you the root of your solution, your equation. And finally, we have x equal to 1 by 10, 1 by 2, 10 minus x cube square root. So once again, you bring this 2 in the denominator to this side. So you get 2x equal to square root of 10 minus x cube. And now you take the squares on both sides. So you get 4x square. The left hand side was 2x. By taking the square, we get 4x square equal to 10 minus x cube. And that is simply again putting this 10 minus x cube to the other side will give you x cube plus 4x square minus 10. So all these three are indeed some fixed point iterations. These are fixed point problems which give you the root of your cubic. Okay, so let's see what we will have with these things, and we are going to take our initial point to be 1.5, which is the midpoint of this one interval 1 comma 2. We are all looking at the interval 1 comma 2, and we are going to iterate these three things. So we will take x equal to 1.5 and apply the g1x to 1.5, then apply g1 square to 1.5 and keep on doing it. We will do the same for g2 and the same for g3. The results are here. So a, remember, is this g1, which is actually the simplest one. All the other functions have square root involved in them, whereas a has a very nice looking fixed point problem. But when you iterate the g1 on a, which is on x, which is 1.5, at the first instance you go to minus 0.875. So we have gone outside 1 comma 2. 1 comma 2 is our interval, and g1 takes the thing outside that. Next time it is going to 6.732. So it has become bigger in the magnitude, and it is still outside 1.2. The third iteration is minus 469.7, so which is very big, and the next one is some 10 power 8. So that is likely to be a divergent sequence. So that sequence does not converge. What happens to the sequence, what happens to this b, which is g2x, which is 10 upon x minus 4x square root. You started from 1.5 and you are going to get 0.8165. So this is also outside 1 comma 2. Next time it is giving you 2.9969. So that has gone. So this 0.8165 was just before 1, and this 2.99 is like almost like 3. So that is after 2. And after that it has gone outside the realm of real numbers. So you are getting square root of a negative number, which is a complex number. So we have gone outside the set of real numbers. Okay, so these two fixed point methods have failed very badly. And now we look at the third one, which is 1 by 2, 10 minus x cube power 1 by 2. That seems to be working well. It is first of all taking everything within the 1 comma 2, the interval, and we see that there is some pattern of that is emerging here. So the last three values, the 20th iteration is giving you 1.365230236. The 25th iteration is again similar, 1.365230, then 006, and 30th iteration is also very close to that. So 1.365230, that seems to be reasonably close to the root of the equation that we started. So the methods A and B failed very badly, and the method C is working quite well. So what has gone wrong? What went wrong? The first of all, these two sequences are divergent in AB because the one in AB keeps expanding in magnitude, so it's going to infinity, and the B sequence B has gone into complex numbers, so that is no more in real numbers. So those are divergent sequences. And actually the problem was that the iteration given in the A is it doesn't take the interval to itself. So we are looking for, we had this theorem called fixed point theorem, and the theorem says that whenever the function takes the interval to itself, then the function will have a fixed point. But this function that we have, g1x, that doesn't take 1 to 2, 1, 2. So it is not reasonable to expect a fixed point for that. Sometimes we have noticed that it's not a necessary condition. Sometimes you may have a fixed point if you get lucky, but many times it will not happen. So g1 of 1 is 6 and g2 of 2 is minus 12. Therefore, the interval 1 comma 2 is first of all put in the other way, and the bigger values are sent to the smaller values, and it has increased in magnitude. G1 increases it, then G1 square will make it even bigger, and so on. So the values will keep going to infinity. The same reason holds for G2 as well. And in fact, we have seen that the iteration in B has taken the values outside the set of real numbers. We saw that there was a square root of a negative number. And both these iterations, both these functions G1 and G2 have the property that the derivatives are not bounded above by the number that you would want. Okay, the third iteration is taking the interval to itself. There is a small problem about the derivative. So the derivative fails to satisfy the condition in the fixed point theorem. But if you observe it very carefully, then the derivative satisfies the condition on this subinterval 1 comma 1.5. And therefore, this sequence works. If you are starting from 1.5, then within this interval, the derivative has the property that it does this particular thing. And therefore, this G3 is a strictly decreasing function. So when you start from 1.5, you will come down by some value, then you will come down, then you will come down, and so on. So this way, it's a decreasing function, and since it is also bounded, you are bound to have a convergent sequence. So those are the nice things that we had. And so this is one very natural question that one can have. That is, whenever we have a root finding problem, how do you convert it into a fixed point problem, which will give you a sequence which does converge to a solution, and preferably also rapidly. We would want the convergence to happen rapidly. So not just slowly, but we would to have like to have a rapid convergence. So how do you really ensure this? And the possible answer is that you manipulate this root finding problem into a fixed point problem that satisfies first of all the conditions of the fixed point theorem. Once the function satisfies the conditions of the fixed point theorem, then you are guaranteed to have a fixed point. And moreover, if the derivative condition is satisfied, then there is a unique fixed point. And you may also hope then that the sequence that you get is a monotone sequence. So with these two, we are going to end this lecture, but I will give you this homework that there are these two further iterations, x equal to g4x, which is 10 upon 4 plus x square root. And then finally you have x equal to g5x, which is x minus x cube plus 4x square minus 10 upon 3x square plus 8x. So here the numerator polynomial is the original polynomial that we had, whose root is the thing that we are looking for, and the denominator of the same rational function is simply the derivative of the numerator function. So there is something which is happening here, and we would see more on this last kind of functions in our coming lectures. So with this, we come to an end of this lecture, and I will see you in our next lecture. Thank you.